Alright, we've been busy and hard at work at applying our beam deflection model, and so we're going to show how to do this in a slightly different way, and that is before we were formally integrating the fourth order differential equation. But what do we really have to do it that way? Could we simplify this a little bit? Right? The beam that we've got is a built-up section. It has two channels with two cover plates. Right? That's what you see here. Right? And we've got bolts that are spaced longitudinally every 7.5 inches. And someone has already found for us, applied the parallel axis theorem to get the second moment of area about the bending axis. That would be shown here as the local z-axis. 883.33 inches to the fourth, right? The total length is 9.52 feet long, right? And so that's kind of a weird dimension, right? Well, the architects sometimes do that. They don't like nice even feet. Let's just figure out how many inches 0.52 feet is, and it's 6 inches and a quarter inch. That's not uncommon. I see this all the time. That's the way that things work out oftentimes. And we have an external couple of 238 kip feet being applied to this composite beam. Alright, well, we know how to go and find reactions, right? We create the free body diagram, and with this counterclockwise moment being applied, then the reactions here, let's call to the left A, and we'll call to the right B. Then, hey, that's just going to be, we have to have a force couple, and if this is length L, then this reaction here will be C over L, and this one will be opposing that at C over L as well, right? C over L times L will be equal to C, and we've got it. Right? So notice that means the shear diagram goes immediately up, C over L, little q. Our distributed load is 0. We don't have one. So that means the slope of the moment diagram is flat, or 0. And we come down and we close off just like we should. Boom, C over L. So there's your shear diagram. And so that does mean, by the way, V as a function of x would equal a positive C over L. And then we're going to have 0 moment here, and it's just going to increase by the slope, which is C over L. It'll end up, C over L times L will be the change in moment. So we're going to end up at C, or in other words, the moment function by observation is just C over L times x. Right? Bam! We didn't have to formally set all that up. We can do shear moment diagrams, and sometimes that's a lot easier to do. Right? And so that's what we're seeing here along the way to figuring out what the transverse deflection expression is going to be. Right? So now that we have this, let's also anticipate what we think the deflected shape is going to look like. We're going to have 0 displacement at A, 0 displacement at the support at B. We've got positive bending moment, so positive curvature throughout, and so the only way to kind of fit that in there is going to be as follows: a nice smiley face throughout the whole beam, right? And so there's your V of x that goes along with the moment diagram. Alright, so now we've already done this step by observation, right? The moment function, that m of x is equal to C over L times x. And then by observation, right, the two displacement boundary conditions. Alright, we already talked about that. V at x equal to 0 is equal to 0, and V at x equal to L is going to also be equal to 0. And now, away we go. Now we're going to do the same old thing we've been doing. That, alright, we've got curvature is equal to m over EI, and m is Cx over L. And there's your EI sitting there. And now we can integrate that to get to slope. Pull the EI out as a constant, and we get Cx over L dx. And so that's going to be equal to 1 over EI times, then, of course, Cx squared over 2L plus our first constant of integration. Actually, it's not. It's our first one associated with our displacements, but we found those other ones from the forces, really we found that right in here. Right? Now, we don't know the slope anywhere, so we can't evaluate that one. So no slope boundary conditions. So that means we just got to go to the next one here. That our deflection is the integral of our slope. So 1 over EI comes out again, and we've got CX squared over 2L plus C1. Boy, I sure hope I didn't make any mistakes there. Let me double check. There's our C over L. I'm going to integrate that. That's X squared over 2. That's what I've got. Good. Oops. Now I just made that look really weird. Alright. So let's keep going. 1 over EI. That's now CX cubed over 6L plus C1X plus C2. And now we can go evaluate using our boundary conditions and find those constants of integration. V at 0 will equal, there's a 0 here, there's a 0 there, and the 1 over EI will go across, so C2 is equal to, well, C2 over EI is going to be equal to 0, therefore C2 equals 0. Always like it when constants go away. And then V at L will be equal to 1 over EI CL cubed over 6L plus C1L, C2 is 0. That's going to be equal to 0. The EI again goes away, and our C1 is equal to a minus CL over 6. And that makes then our transverse deflection expression, for which we were searching, 1 over EI, our CX cubed over 6L minus CLX over 6. And again, I always check my units here. CL cubed over L is CL squared. CL times L would be CL squared, so that's the same units. And the C is foot kip. So foot kip, that's a CL squared, so that's foot kip times foot cube or foot squared, so that'd be all kip foot cubed over EI, which is going to be like foot kip foot squared. So we're going to get units of displacement here. Length units are going to be the key. Alright, now to find the maximum, let's go back. We now know what C1 is, so this is 1 over EI CX squared over 2L minus CL over 6. Right, now we can find where theta is equal to 0, right? V max at C or at theta equal to 0. So that would be 1 over EI CX squared over 2L minus CL over 6 has to be now equal to 0. And what are we going to get here? Well, the C cancels out. That's interesting. The L is going to go over to here, and we'll have X squared equals L squared over 3, or X is equal to, now the negative value makes no sense here, L over the square root of 3. That's interesting. And so that means that our max displacement will be at V equal to L over the square root of 3, and so that's 1 over EI times C, let's see, that's C over 6L, and then we'll have L over the square root of 3 cubed minus CL over 6 times L over the square root of 3. So that'll be CL cubed over L, so that's CL squared. So there's a CL squared that's in here that gets factored out over EI. And then this becomes 1 over 6 times 1 over 3 root 3 minus 1 over 6 times 1 over root 3. Well, that's interesting. The 6 comes out too, and we're just left with then, and the root 3 would come out, and we'd be left with 1/3 minus 1. I took out the 1/6 and the root 3. That's a minus 2/3. So the 2 goes away to that, and that becomes 9. So that means our Vmax is equal to a minus CL squared over then 9 root 3 EI. I think I did all that math correct. You'll be sure to let me know if I didn't. The negative sign means, of course, it's downwards. That makes sense. So all the other numbers are going to be positive.